All right. Now we're going to do. I'm just going to give a brief introduction to mass spec. Okay, so this is something that you guys are going to need for your quiz that's coming up on Wednesday, and this comes from section 13.24 in your book. So what is mass spec? Mass spec is identifying not just parent ions of fragments that come through the mass spec, but it also is important in identifying fragments. And from those fragments that we can see on mass spec, we can determine the structure of whatever comes flying through. Now the way a mass spec works, it works the basic varieties, and we're not going to talk about anything that's a little bit more complicated. But the basic varieties take something in the gas form, so it heats it up so that it's a gas at that point. And when it's a gas, it fires it into the mass spec detector at that point. Now, the way the mass spec works is the gas comes through, and as the gas comes through at this point, it's being bombarded by electrons. So here's the gas, gets bombarded by electrons. Then it gets put into a charge tunnel. That charge tunnel is going to have a positive and a negative end. And as these electrons come down and bombard the gas, they're stripping electrons away from the molecules that come through. And in stripping those electrons away, it gives it a positive charge. Okay, it becomes a radical cation. So as these molecules come flying through, if they are a cation form, they're going to be repelled by this side of the tunnel, which is charged positive, and the other end of the tunnel is charged negative, and that's going to attract the cation. Now, as this comes through, the goal of the fragments or the parent molecules that come through the mass spec is to come down and hit the detector. Okay? If it hits the detector, it can be detected and it reports a value of whatever's flying through. Now, the way to hit the detector is that it's got to navigate this tunnel. It's got to navigate the tunnel perfectly. If it's too heavy, as it comes through and tries to navigate this tunnel, if it's too heavy, it's going to come off here at the end and it's going to hit and it's going to be knocked away and it's not going to be able to hit the detector. If it's too light, what ends up happening is it comes through and it gets attracted too quickly to the negative side. Then it also gets knocked away. It doesn't get to the detector. Only things that are in the Goldilocks zone, have just the right mass, are going to be able to come through and hit the detector. Okay? Now, in general, whenever the detector sees something, it sees something in a mass to unit charge ratio. The mass to unit charge ratio, mass of whatever is being shot through, the unit charge, generally it's a +1. Okay? Sometimes you get a +2, depends on the molecule. If you're doing liquid LCMS, this number is usually quite large. It's usually 3, 4, depending upon the molecule you're using. And that's useful for analyzing biological samples. But for our sakes and purposes, we're just going to use something that has a mass and a unit charge, which is generally 1. Okay? So as these molecules come through, they go through electron impact. The molecule itself loses one of its electrons. And in losing one of its electrons, it gets that positive charge. And now once it becomes this positive radical, it's going to start falling apart. And there's two possible things that can happen when it falls apart. It's going to fall apart to a fragment that's a radical, so you get a radical fragment over here. The other half is that as it falls apart, it's going to become a cation. These are the ones that we're going to be able to detect with the mass spec. Obviously, radicals don't have any real charge, so in doing so, they're going to fly off into space. But the cations are the ones that we can control the path of over here in the mass spec. Okay? So to give you an example with butane, as butane comes through the GCMS, it comes through the GC, it gets into the mass spec portion, it's going to be blasted with electrons. And we recognize that by first putting this little bracket saying I've got a positive charge and a radical. This just means that somewhere on the molecule, I don't know where, we've lost an electron. Now we're expecting this thing to break down. Okay, and there's 3 different locations, 1, 2, 3, that can break down from this thing being hit by electrons. Okay, I can break here, I can moment the breaking bonds, so I can break this bond, this first bond, I can break this second bond, and if I break this third bond, it's going to give me the same type of thing because butane's pretty symmetrical, so I'm going to see the same thing on the other end. So from point 1, alright, from point 1, what I'm going to see are 2 possible fragments. I can see this propyl radical, or the CH3 methyl cation, or I can see the propyl cation and the methyl radical. I always get those pairs. Okay, so I can always see both of the fragments that come off of this thing if this thing starts breaking down. The second part, if I see this come through, I'm going to see an ethyl radical, and I'm also going to see an ethyl carbocation, or an ethyl carbocation and an ethyl radical. So I didn't have to write this second half because it's symmetrical, and I'm going to see these fragments coming off regardless. Okay? So, what am I going to see as far as concentration goes? Now remember stability with your radicals and carbocations. If you have a radical, and I'm going to write carbocation up here too, because they're both the same, alright? Remember that tertiary was more stable than secondary, which is more stable than primary. And for mass spec, you can put another thing in here, which is more stable than the methyl radical, or the methyl carbocation. Okay, so anything that's less stable, I'm going to see less of, as far as concentration goes, in the mass spec. So my major peaks, what I'm going to see, if I look at this, this is primary, that's primary, again, not very stable. Okay, this one, this propyl over here, is going to be primary as well, but the CH3 is a methyl, which means it's going to be harder to break that bond. Okay, so now I've got these two propyl groups. The propyl groups give me a 29 mass. C8, see this was 12, this is 12. 3 hydrogens gives me 27, 2 more gives me 29. So 29 is the major propyl fragment that I should see. Okay, the CH3 is 15. Okay, that's the methyl radical that I see flying off. Depending upon the molecule, that can be common or that can be uncommon. I'm not thinking it's going to be too common here because it's generating a propyl cation or a primary cation. Okay. The other thing I could see is also the propyl cation for 40, and that comes at 43. Now notice there's an easy way to keep track of this. Methyl weighs 15. If you add a CH2 to it, you're adding 14. So that's 29. If I've got a propyl, I add another 14 to this. That gives me 43. So that's what I should see on my mass spec. Alright, now here's pentane. I couldn't find butane on the STBS. So I decided to use pentane. They're very similar. Okay, here's pentane's molecular formula. Now the first thing we expect to see on electron impact is that we should see if the molecule itself is relatively stable, like pentane is, we should see the parent ion. The parent ion is at 72. Now if you look down here on the bottom scale, we've got down here 70, and over here we've got 72. Okay, 72, that's the parent ion of pentane. Now the fragments that are coming off, we should see breaking there, so I should see a methyl coming off and a butyl, so I should see 15 and I should see 57. Okay, and sure enough here I see the butyl. Note that down here I don't see anything really with 15. This is usually an artifact of this thing being so light that it's hard to actually capture those. Not to mention methyl, not a very stable form. Alright, so I see the butyl down here at 57. If I fragment in this location, I'm going to see an ethyl group and I'm going to see a propyl group. Alright, propyl comes at 43, and wow, look at the 43 here. So I've got 41, 42, 43 right here. So up here, this is the propyl. And I also expect to see something at 29. At 29 here, I've got the ethyl group. Okay, it's important to note also that I've got one off here, and this is something that frequently happens in mass spec. I lose hydrogens as well. So down here, I'm losing some hydrogens down in this area. Okay, don't try to detect anything from that. Look for the major peaks. The rest of these are artifacts of the major peaks, as in a hydrogen was lost somewhere during the flight time of this molecule. Okay, I also want to point out down here, if you look down in this region, you see that there is some C13 residue that's on this particular form. Alright, so C13 is a peak that's down here. The more carbons you have, the larger those peaks get. But remember, you should see what's called a C+1 peak, or a carbon 13 peak that shows up on the mass spec.